All right, this is lesson 2.3 out of your college algebra text. It's more things about graphs of functions, and so we're going to use this section to come up with more ways we can describe functions. Let's talk about this piecewise function here. What they want you to realize here is that we can use function notation. This is function notation, and we should be able to use a graph to find those outputs. So let's do that first one, g of negative 2. G of negative 2 is talking about when x is negative 2, what is the y value? So negative 2, 0 being on this graph can be used to say that g of negative 2 is equal to 0. So we shouldn't have equality here. Let's use an arrow. These are equivalent statements. Look at the next example. If I have g of 0, that's talking about the ordered pair when x is 0. In this case, the y-coordinate is also 0. So I could say that g of 0 is equal to 0. Finally, we have g of 2. G of 2 is talking about the y-coordinate when x is 2. So when x is 2, we're looking at that ordered pair, 2, 4. So g of 2 equals 4 is the equivalent of saying that 2, 4 is on the graph of the function. All right, now to find the domain and range, we are going to first look at what possible x values we have for this function. And notice that if I compress this onto the x-axis, all x values are accounted for. So I would say that the domain is all real numbers. Looking at the range, let's compress this graph onto the y-axis. Starting at the bottom, we see all y values accounted for, every single number less than 4. So then we would say the range is all values y less than or equal to 4, or we could use interval notation, negative infinity to 4. All right, part of this function, or part of this section has you look at equations of circles. So here is the general form. This is an equation of a circle centered at 0, 0 with the radius r. And what's nice about this is you can get y by itself to define in terms of y. So y squared will equal r squared minus x squared. And then so y equals positive negative square root of r squared minus x squared. The positive aspect of this accounts for the upper half of the semicircle, and then the negative component accounts for the lower half of the semicircle. So let's graph a couple of these. So for this first example, we would recognize that once again, your standard form is r squared minus x squared. So we can see that the radius is going to equal to the square root of 4, and it's going to be the upper half because it's the positive. So here I have a semicircle of radius 2, and that's the graph of it. On the next example, I would see that, let's see, if r squared equals 9, then r equals 3, and the less than accounts for the lower half. So that would be an equation of a semicircle on the bottom half of the x-axis. All right, so terminology, increasing, decreasing, and constant. A function is increasing if the y values, the f of x values increase from left to right. So the increasing part of this is going to be from A to B, and then from C to D. And then the decreasing part of this, if the f of x values decrease from left to right, will be from B to C. There is no part of this example that is constant. If I added on a constant part, it would look like this. The constant mean it's a straight line from left to right. So let's take an example of this. Here is a piecewise function. Let's graph it first. Let's see, if x is less than negative 2, it's negative 2. So I would have this part of the graph is going to be the constant function of negative 2 for all x values less than or equal to negative 2. The graph of negative x is a y-intercept of 0 with a slope of negative 1 from negative 2 to 1. So it's going to look like this. oops, I do need an open circle here because of the inequality. And then let's see, this third part is a quadratic function. It's a quadratic function shifted to the right 2, so the vertex is at 2, 0, and then I need to graph this for x values greater than or equal to 1. So here is a graph of the piecewise, and we can use this to find intervals that the graph is increasing. So we would say that this graph is increasing on intervals. Let's see, going uphill from left to right, there's only one place. So let's see, that is the interval, all x values greater than 3. One thing we do note here is that it does say open, so we do want to just write this as 3 to infinity. For decreasing is when the graph is going downhill from left to right. Let's see, the decreasing would be this linear function here, and then the part of the quadratic function there. So we could say that this is decreasing from -2 to 1, and then it's also decreasing from 1 to 2. For constant values here, we would recognize that, let's see, constant, that's going to be when the graph is horizontal, and so we would say it's going to be -infinity to 3. Excuse me, -3. All right, many times they'll just give you the graph of a piecewise function, and so let's use this graph to find intervals where it's increasing. So once again, we're looking for places where it goes uphill left to right. So that would be this section of the graph, this section of the graph, and this section of the graph. The important thing is we acknowledge where the x values, the intervals of the x values where it's increasing. So it'd be this interval here, all values of x less than 3, and then all values from -1 to 1, and then all values from 4 to infinity. Let's write that out. So that's -infinity to -3. Let's union that with -1 to 1, and then we're going to union that with all numbers 4 to infinity. So these are the 3 intervals where this graph is going uphill left to right. Looking for decreasing values where it's going downhill, I see only 2 places. The x values that are from -2 to -1, and let's see, x values that are from 3 to 4. So these 2 intervals are places where the graph goes downhill, and then the only place where this graph is a horizontal line, meaning a constant function, are going to be x values from 1 to 3. All right, so here's another 2 more examples. One thing we haven't mentioned here, let's look at part A. It says find domain and range. Let's do number 23 here. The domain is compressing this onto the x-axis. So I can see that this has x values all the way from -1 to, let's see, 1, 2, 3. So the domain of this is going to be all real numbers from -1 to 4. Compressing this onto the y-axis, we can see, starting at the bottom here, we can see y values from -1 all the way up until 3. So the range here is going to be from -1 to 3. And from the graphic approach, it's easy to see that. But now let's find those intervals. The intervals where a function is increasing and decreasing is always measured from or expressed from the x-axis. And so here we have the increasing part would be this section of the graph and this section of the graph. So let's grab those the intervals from the x-axis where we have the increasing portion. So we would say this graph is increasing. It looks like from -1 to 1, and I'll just union that with the interval from 2 to 4. The section of the graph where this is decreasing, going downhill, is this portion, And notice how small that interval is. It's from 1 to 2. So I would say this function is decreasing upon the interval from 1 to 2. All right, also in this section, we need to talk about local maxima and minima. With any function, you're going to have peaks and valleys. So we think about these peaks as being maximum values, and we think about these valleys as being minimum values. In this particular example, there are 2 maximum values located at these 2 points, and there are 2 minimum values located at these 2 points. A relative maximum occurs when the function goes from increasing to decreasing. So we can see this graph is increasing up until the max and then starts decreasing. A relative minimum occurs when the function goes from decreasing to increasing. So as I continue along this curve, it's decreasing, then starts to increase, giving me a minimum value. All right, so here are 2 functions. Let's identify what these local maximum and minimum values are. So I only see one local maximum located right here. So I would write this. I'd write the local maximum. And here's the deal. The maximum is the y-coordinate. So if I write this ordered pair out, this is 0, 2. That 2 is the max value. So the local maximum value is equal to 2. And we would normally say at which x value it occurs. And we would say at, or let's say when x equals 0. All right. There's 2 minimum values. The local minimum values are here and here. And writing those ordered pairs, I get -2, -1, and then 2, 0. So writing that out, I would say there is a local minimum value equal to the y-coordinate of -1, and I would say when, the location of that would be when x is -2. I would say there's another local minimum value equal to the y-coordinate of 0, and the location of that is when x equals 2. All right. The second example here has the vice versa of that. We see 2 maximum values. Let's find those. The maximum values are located at the peaks. So let's say this. We have max values. Let's say a max value equal to the y-coordinate. Once again, this highest point is 2 on the y-axis. And we would say when, where it's located, when x equals -2. We would also say there is a max value equal to, the maximum value is that highest y-coordinate of 1. And we would say where it's located, when x equals, let's see, that x-coordinate is 2. All right, I see one minimum value. That's located right here. So I could say that there's a minimum value. And once again, we want to be careful. These are all local. That's the term we're using here. Local, local, local. Local, there's a local minimum value equal to the y-coordinate. The lowest y-coordinate here, the ordered pair is 0, -1. So that -1 is your minimum value. And we would say that happens when x equals 0.